I'm going to try and motivate it a little bit and then sort of just get straight to the point. So far we've done traversals. Remember that this big picture part of this course is graphs. And what we're trying to do is understand what kind of problems we can solve with graphs by looking at generic problems in graphs, and then the solutions to those problems turn out to be general solutions to many kinds of problems. So that's the big picture. So far we looked at traversals, and that's good for testing connectivity and reachability and so on. Now we're going to start looking at something called spanning trees. Now, before I get there, let me try and motivate this with a problem. Suppose you're trying to build a new housing scheme. Naturally, if it's a housing scheme, it needs water. In the 21st century in Jamaica. And that means that you need to have, the reason part of the permit that you get when you get that permit to build is you're going to need to negotiate with Water Commission what size pipe you need to get to your property. After that, it's kind of up to you and your plumbers to lay down the pipes that's going to be able to reach all the houses. Now, of course, you can imagine if I said to you, okay, so suppose you're the developer and you're being consulted. So where should I lay these pipes so that everywhere that there's going to be a house can get sufficient water for that house, and yet I will minimize my total cost of laying pipes? How do you solve that problem? Don't feel qualified? Getting paid big money to answer this? No? No? Well, all right. So after today's lecture, I hope you can answer. So what you're looking for is to build a network of pipes. And you want that network to be able to reach every house. First of all, let me ask you this. Can you think of a way to represent this as a graph problem? What are the nodes? Houses are the nodes, okay? What do you think would be an edge between two? All right, where you put a pipe might be an edge, but remember that you're going to decide where to put the pipes after. So the nodes, the houses are sitting there. They have some connection before you decide where to put the pipes, no? Sorry? Where do pipes normally get laid? Just anywhere? Through the backyard? Just, sorry? Yeah, along the roads, right? So in other words, it needs to be accessible. So first of all, you would have cut the roads to reach the houses, and then you'd have contemplated where to lay down your electricity, where to lay down your water pipes. And it's going to be constrained by where the roads are, because the equipment that needs to lay those things needs to use the roads to get there, yes? So in fact, what do you think would be the edges now then? Not where I have a pipe, where I have roads. Good. So two houses will be connected if they're connected. The two nodes that represent houses would get a connection between them if there's a road directly between them. That kind of makes sense. Right. And now you want to know, where should I lay the pipes? So which subset of these roads am I going to dig trenches to lay pipes? Understand the question now? And of course, if pipes are costed by their lengths, and of course, maybe, in fact, not just the length, but the girth as well, because a certain capacity pipe, a big fat pipe, is going to cost more than a thin pipe, just because you use more material, for example. Also, the market value of it will be different because the demand is different for the same length of pipe. But if I'm not interested in finding out, how do I minimize that cost? What I need to do is decide which subset of these roads I'm going to use that will reach every house still, and allow for the total cost of all these pipes be minimal. That make sense? Correct. So the graph is going to be weighted. What do you think would be a good value for, what kind of function would determine the weights in this case? The what? The length of the road might be one, the cost of the pipe might be another, right? So the amount of water is going to be part of the constraints. That's going to determine what minimum size pipe I can use. And then that will translate into a cost. You kind of have to focus on one number in order to use the algorithms that we're going to talk about. But that problem you're trying to solve is called a minimum spanning tree problem. You're trying to select a subset of edges that will touch all the nodes. And in this case, because that's just a spanning tree, what we're trying to do is minimize the total weight. So then that's called a minimum spanning tree. Got that? You're supposed to say yes at that point so that I can. All right. So here we go. Let's document that so that you have it in your notes. So actually, all my definitions are going to be relative to a given graph. And so let me just set that up first. Given a graph, and it has to be, by the way, it must be an undirected graph. If you have a directed graph, you can't normally talk about a minimum spanning tree, not in the normal sense of the word. All right, so given an undirected graph, we'll just once and for all say that the number of vertices is n, the number of edges is m. We won't need it right now. I'm gonna probably make reference to it, but in case you see me reference n and m, this is what I mean. N is the number of nodes, m is the number of edges. Let's write down some things that we just covered. So first of all, a spanning tree call it T, is a subset of edges. Such that every node in V is incident on an edge in T. You know what incident means? Silence means consent, right? So that means a yes. What is no? You don't like the idea that silence is consent? Yes, that's why I asked. Nobody don't say anything, so I say, all right, Jing must be cool then. I know, no, that's what I'm asking, if you understand. If you don't, then you just say no, please explain. So a node is incident on an edge if it touches that edge. That's what it means to be incident. Okay, so edges are pairs of nodes, yes? So a node is incident on an edge if it is one of those two endpoints. That's what it means to be incident. All right, so in other words, if I were to, that's in words, if I were to write this in math speak, then what I'm really saying is that for every vertex, I'll just use a lowercase u because it's on the board, it's clear. So for every vertex in V, then either, well, I should say it like this. There is another side to it. There's a node V such that UV is in T. Remember, it's undirected. So UV and VU is the same edge. And all this says is, pick any node in the whole graph, there will be an edge in the tree that touches it. Okay, that makes sense? So that one line is what all of this was trying to say. Well, except the spanning part, because this doesn't say what T is. T is a tree. If T is a tree, what can I say about the size of T? How many members? Since T is a subset of E, how many members are in T? What's the size of T? This is from your discrete maths now. If I have a tree that touches n nodes, what? It's n minus 1. Okay? You did that in discrete maths, no? I think so. There's one comment I should have made at the very beginning when I set this up. It was a brief oversight. Let me try to correct it now. It needs to be a connected graph. If it's not a connected graph, obviously I can't span the whole graph with one tree. I would need multiple trees. I need a tree per connected component. To simplify the discussion, we often talk about doing a minimum spanning tree on a connected graph. So here, let me insert connected here. Right, so that's a spanning tree. The value or weight is just the sum of all the edges in that tree. Okay, so the weight of the tree, actually I'm going to use lowercase w. So then the weight of the overall tree, technically speaking, I should be doing this because the edge is a thing and the weight is a function of that thing. So the weight of the overall tree is just the sum of all the edges in the tree. That's what you'd expect. So a minimum weight spanning tree is what you think it is. A minimum weight spanning tree, MST for short, is a spanning tree whose total weight is minimum or the smallest among all spanning trees of the graph. Okay? So, in the question that I started with, you have this housing scheme, you need to lay down pipes, you have your roads between the houses. There are many, many ways you could possibly, well, usually, especially if you graph, you know, if you imagine a housing scheme that isn't, if the road network itself is not a tree. So, in other words, you have loops and you have roads meeting roads, and there are ways to get alternate routes between points. As long as you have that, then in fact you'll have multiple ways you could create a spanning tree. But sometimes, this is not always true, there will be a unique minimum weight spanning tree. Sometimes the weight, the minimum spanning tree is not necessarily unique. In those cases, that just means that all those various spanning trees have the same minimum weight, but they might be different trees. They might use different edges, but the total weight is the same. In some instances, you may choose, you know, they might all be equivalent. In other instances, there might be other considerations you'd bring to bear to make a decision between multiple minimum spanning trees. So anyway, that's the problem. That's how we represent it in a graph, as a graph problem. That's the application of why you might want to solve it as a particular example. Now let's talk about how to solve it. So all up until now, all I've done is identify what the problem is. Define it in a very rigorous way, but now I need to talk about how you can solve this problem. Okay? Now I don't know if you did this in discrete maths. No? Okay, good. So you're about to learn something then. All right, so the question is, how would I go about constructing a spanning tree that's minimum? That's ultimately what we're trying to describe. Now, there are two algorithms that we're going to cover. These are the two primary ones that I know of, that I'm aware of. I'm not going to say that these are the only ones, because obviously you could have brute force. I could just try all possible trees. I hope by now you've come to appreciate why that sounds like a bad idea. No? After all these weeks? Anything that sounds brute force, you ought to think, you should, yeah, if somebody's trying to sell you something that says it's the best thing since sliced bread and it's brute force, it might be true, but you should think you should be highly skeptical. Highly skeptical that brute force is going to be a good thing. So, yes, you could do brute force, but we're not going to talk about brute force. So let's talk about Prim's algorithm first. And what I'm going to do is start, rather than give you the algorithm, I'm going to start by trying to illustrate for you why it's true, why it works, why it's so. All right. So here's the basis of Prim's algorithm. Suppose that or maybe I'll tell you what the general idea is. In Prim's algorithm, what we're going to do is start from some node. It doesn't really matter which node you start from, but we'll have to say where to start from. It will have a start point. So this is kind of similar to how the traversals work. You start from somewhere. But here's what we're going to do each time. Where we start from is committed to being part of the tree. At the end of the day, we're trying to construct a spanning tree. So we know we need to get all the nodes into the tree. That's the job. That's the objective. So when I start with one node, there's no harm in saying that this node is part of the tree because the objective is to get all the nodes anyway. So I can start from anywhere. But when you start from one place, here's what the algorithm tries to do on each pass. It's going to try and identify a neighboring node that's going to be the edge that we want to put into the minimum spanning tree that connects what we already have in our tree. So at the very beginning, I only have one node in my tree. I'm going to try and find a node that connects to that node. But as my tree grows, I'm not necessarily looking for a node that connects to the same node I started from. What I'm looking for is a node that connects to any node in my tree so far. So the idea is I'm growing a tree one node at a time. And each time I select a new node, what I need to do is assure myself that I never need to go back and change my mind. So when I pick a node to put in the tree, I want to be certain that it must be the best choice at that point in time. And not only was it just best at that point in time, because that sounds like greedy. I remember greedy don't always work. Not only is it the best at that point in time, I want to be able to prove that I couldn't have done better. It must be the right thing. It needs to be there. All right? So the general idea is I want to select, I'm going to grow a tree one node at a time. Here, let me use my abbreviation, MST. Now here's a question. How do we select that node to choose whenever we're ready to do this process? Here's the idea. So imagine that all of this, I'm going to draw two, tell you what. All right, so here's my graph. That's the graph, that's the space the graph is living in. And I'm going to have selected some nodes maybe those are the nodes that I've selected so far. That's the tree that I'm building up. Now, among the other nodes in this graph, there will be some connections to this tree because it's a connected graph. So here I have some edges going off to perhaps multiple nodes that are sitting outside of my tree. I haven't made up my mind yet which of these possible candidates is the next one to take. You understanding the picture so far? So everything inside of what I labeled as T is committed to being the tree. Can't change my mind. Those edges are part of the MST. When I look at edges that connect to those nodes, I recognize that I have a bunch of candidate nodes here. Remember, I'm trying to select one more node to add to my tree. So the node I'm going to add to my tree has to come from one of these adjacent nodes. Okay? Now, if you're working with a textbook that you're prescribed to use, they call this collection the fringe. Doesn't really matter what you want to call it. The important thing is you recognize that we have a collection of nodes that are, for all intents and purposes, just like the discovered nodes when we're doing the traversal. Those nodes are among the next set to choose to commit. So if you think of these just like the visited nodes in our traversal, these are just like discovered, and the nodes beyond those are just like unseen. So that same category 3 statuses also applies to this process, even though we're not doing a traversal. Now, how do I choose among these? So I'm going to call this the fringe. And for this purpose, I'm just going to call it F. So we need to select a node from F. And here's how we need to select a node from F. How do we do that? Here's the idea behind it. Select the node that has the minimum weight that crosses the tree to the fringe. Why is that good? Why is that guaranteed to be the best choice? In fact, guaranteed to be an irrevocable choice, meaning you don't need to change it. You don't need to reverse that decision. Guaranteed that when you choose the lightest edge that crosses from T to F, it's guaranteed to belong to the minimum spanning tree, or minimum spanning tree in case it's not unique. Why? I should say what the U is. Oh, like this. I tell you what. I know you're gonna get confused. Let me do it like this. Change those variables. Because you're gonna think that U over V, UV here meant the same as UV here. No. So let me say it like this. Weight of IJ, where I is in T and J is in F. Okay? You understand what I just said here? Okay. Silence is consent. So yes, that means yes. Great. All right. So it's fairly simple. What we're looking for is the lightest edge that crosses T to F. Now I ask the question, why is that true? Why is that the right thing to do? Any ideas? So that's actually true, but that doesn't explain why that's true. But that's a good try. That's a very good try, actually. So what young miss at the front said is that that's when you choose that, it's going to guarantee that you get the lightest tree overall. And you're saying something about there's no other path that's going to be less, but there's not going to be. Let me make sure I understand. So suppose we end up selecting this guy as V. So this edge must have been the lightest one crossing the fringe. What are you saying? There's no other? Okay, so you're saying path, but it's not path. If we choose a different node, that wouldn't be able to get us a lighter weight tree. All right, now let's examine why that's true. So you see, let's say that edge is the lightest one. Yes? Now, what we're claiming is when you include it, you will get a minimum spanning tree. Let's consider the alternative. Suppose, for simplicity, okay, first of all, I could take all three cases. So we said that this is the lightest edge. So obviously there are no other edges that are lighter than that one. That's what it means to be the lightest. All right. So then there might be some other edges with the same weight. Yes? But if they're the same weight, then that means that that node could have also been chosen. So what we really need to contemplate is, according to this anyway, because we just said pick a node that has the lightest weight. We didn't say how to choose among them. In fact, we don't care. So what we really need to debate or discuss or prove is that what if this is the lightest one and is unique? So the others are actually weighted heavier than that lightest edge. You with me so far? So the question is, why would this one, when I select this, guarantee that I'm on the right track to picking the right minimum spanning tree? Well, let's examine what happens if at the end of the day, let's pretend that, so this is how you do it, you argue by contradiction. You say, suppose that you had some other way and you didn't select that edge. Remember now, this was the lightest edge among all of these. True? Now, let's say that somebody says, no, I don't need to select that, and I have a minimum spanning tree, by the way. Here it is. Now, they're presenting you with a T prime, a minimum spanning tree that they claim to be minimum. You agreed? And they didn't use this edge, and it was a unique minimum edge at the time. Because it's a spanning tree, so they give you some tree T prime and tell you, yeah, this is a minimum spanning tree. You didn't need to use this edge. Because it's a spanning tree, it must mean that they've connected all these nodes with these nodes, because the tree at the end as a spanning tree must connect all the nodes. Yes? Yes? Spanning trees touch all the nodes. So if somebody hands you an alternative tree T prime and says, here's a minimum spanning tree, don't believe me. Work with this other one. Whatever they give you must have connected all these nodes in the fringe with all those nodes in the tree. Somehow. In other words, they must have used one of these edges because we contemplated all the edges are crossed from the tree to the fringe. So if they now chose some other one, let's say, for example, they selected, nah, we could use this one instead. This one I'm going to mark in red. Because at this point in time, we knew that the one in blue was the minimum, its weight is less than that one. Now notice that, so they've handed you a tree, it doesn't use the one in blue, it uses the one in red. Notice what I can now do. Because it's a tree, I am guaranteed, remember that in a tree, all the paths between nodes are unique. You learn that in discrete maths, I think. What that means then is that this bridge is the only way to get from nodes in the fringe to the tree. That means that if I were to now add UV, I've created a cycle. But I can restore my tree by swapping. So I could put in the UV and take that edge out. And I would get back a spanning tree. Because the thing on this side must have been spanning, and this side was obviously spanning. So this was the only link between those two trees. I just swapped a light edge for a heavier edge. So I just constructed another spanning tree, and its weight is less than the one that the charlatan was trying to hand you, the T prime. So therefore, what they're giving you as T prime and saying, oh, this is a minimum span tree, could not have been minimum because I just constructed one that's lighter. So that's a contradiction. Okay, so you must take that one. So Prim's algorithm simply says, okay, so let's organize our structures so that we always take that minimum. What do you think? Now you guys are supposed to be experts at handling data structures that look for minima and so on. So I'm going to organize these nodes into some data structures so that I can quickly find the minimum weight edge at each step of the way. And each step, what I want to do is add it to the tree, and then of course I'm going to then explore the neighbors of that new node I just added, add them to the fringe, and repeat. What data structure do you think I should use to manage my fringe? Excellent. A heap. That's the data structure. If I want to ask more generally, what ADT do I use to manage my heap? A what? No. Binary heap is a data structure. That already. A what? Priority queue. Priority queue. Okay? So we can solve this by implementing our fringe as a priority queue, preferably supported by something like a binary heap, or there are other kinds of heaps as well. Especially for this process, there's something called a Fibonacci heap, which is on average much better than a binary heap for very large graph. But the point is, we want to use some data structure other than don't use a linked list for managing your fringe. Right, so Prim's algorithm basically says, you're gonna start with a node, and then until, who is Neo? Just load him up for me. All right. All right. Add all neighbors of U to a priority queue ordered by the edge weight. And then repeatedly select. So to repeat this process. All right, so let's do an example. Oh, you don't need an example. Can I just go straight to Crisco? Well, you know, when I don't get the interaction, it feels like I'm talking to myself. All right. So let's say that our graph looks like I understand. Okay, so there are some weights on our graph. Question is use Prim's algorithm compute minimum spanning tree starting from node V1. So we're going to set it up to look just like the traversals that we talked about. But instead of labeling it tree, visited, we're going to label it tree. These are nodes that we've visited, not context. I still want to know which edge is responsible, so I'm going to put my source column. And now I might care about the weight because maybe I need to know what the total weight of the tree is, if that's what's asked. If I ask it to calculate the tree, I want to tell me about the edges in the tree. If I ask you to calculate the weights of the tree, I want to add up the weights and tell me what our number is. And over here, I guess I'm going to need this space. So I'm going to call this the fringe, but you should remember that it's really a priority queue. And so, just like we said, this is just like visited in traversals, and your fringe is just like your discovered nodes in a traversal. So we're starting from V1, so we wouldn't have any source. And of course, since you don't really have an edge, then there's no real weight to that. You immediately add what nodes you discover from V1. You see we can discover V2, 3, and 4. Yes? And now we need to indicate what weights so that we can keep track of this. So I'll just add them. So I'll have V2 from V1 with a weight of 2. I'll have V3 from V1 with a weight of 10. And V4 from V1 with a weight of 12. So notice those 3 elements are in the priority queue right now, V2, 3, and 4. And associated information is where they're coming from, and the priority is what the weight on the edge is. Got that? It's a priority queue, so we're going to do a delete min to get that minimum. We're removing from the priority queue, and you're going to add it to, wait, oh, oops. Remove the minimum from the priority queue and add it to the tree. That step was missing. Right, so remove the minimum. The reason I'm removing this one is not because it's at the left, but because the weight is the minimum. So right here I need to remove. Yes, coming back. So when we remove that, that means it's equivalent to visiting. So we add V2 to the tree. We note that it came from V1. The weight that we added with is 2. This is kind of redundant. It's just there to highlight what that weight is. But now I'm going to, because of priority queue, here's what I need to do to manage this information. This is what's currently in the priority queue. I need to potentially make updates to that. Earlier when we did the traversals, there were questions about, should I add duplicates, or am I gonna go in and make modifications to what's there already? When we're talking about FIFO and stack, typically you don't go back in and modify anything that's in there. With the priority queues though, we're gonna need to do that. We're gonna need to be able to go in and make a change because we're gonna want to update the priority that we have for a given node. That priority being, think of this as being, what is the lightest weight edge that we know of that would connect this node to the tree? So far, the lightest we know that would connect V3 to the tree has a weight of 10. And what we want to do is, if we ever discover V3 with a lower weight, we want to update that. Now put another entry in. Pragmatically, if you're implementing it, of course, there are ways to get around that. You can put a double entry in, and then when you pop it out, make sure you didn't already take it up. That's another way you can take care of that. But this way, then you have to have a special kind of priority queue that allows you to modify. So that's what I'm going to model in my description here. So what that means is I'm going to copy down what information is already there. And then I'm going to examine what V2 can discover. And if it's anything new, then I'll add it. So for example, V5 gets added from V2 with a weight of 1. And anything that was already there, in this case V3, the weight is now 3. That's an improvement on the 10. I'm going to mark that up as an improvement. So how do I do that? So discovering V3 with a weight of 3, I'm going to do this. I'm going to say this is an update with a weight of 3, and now I'll be coming in from V2 instead of V1. V4, well, V2 is not seeing V4, so that doesn't get changed. V5 is new. I'm going to add that. From V2 with a weight of 1. So now again, remember this is a priority queue. I'm selecting my minimum. Which node do you think I go to next? V5, that's right, because the weight is 1. So here we put in V5, coming from V2, its weight was 1. Just write back what you currently have in the fringe, and then update by doing the visit, the exploration from V5. Okay, so V5 can see V4 and V6. I already have 1, 2, or I also can see 3. Well, 3 is not an improvement on this direction, so nothing happens because this is a 4. I already have V3 in here with a 3, so ignore that. V5 is looking at V4 with a weight of 5. That is an improvement, so then we would want to update this. What's the weight? 5. Yes. And V5 can also see V6 with a weight of 3. Yes? I don't think I left out anything. I hope I didn't leave out anything. All right. So now you're going to select the minimum. Minimum, there are 2 of them that have minimum weight, or 3. You can select either one. Just for sake of uniqueness, let's just say that when there's a tie, we'll take the one with the lower numbered index. So in that case, I'm going to select V3. This is coming from V2. Its weight was 3. Put back what was in the queue. And then do your this process is called relaxation. Do your relaxation from V3. Let's see, V3 can see, so 2 is gone already, 5 is already in the tree, so we're only interested in 4. But its weight is 8, that's not an improvement, because we already have 4 with a 5, V4 with a weight of 5. So nothing new happens when we explore from V3. Repeat, you're going to take out the minimum, then we add V6 to the tree. Notice now that's from V5 though. The weight was 3. What's left in the priority queue is V4 from V5 with a weight of 5. V6 is not adding anything new because what's left in there? V4. This is a weight of 4. Oh, that's an improvement. So then now we get V6 with a weight of 4. So when we remove this, this comes in as put in V4 from V6 with a weight of 4. So where's our minimum spanning tree according to this procedure? It's V1 to 2. There was 2 to 3, or actually 2 to 5. There was 2 to 3. What else? There's a 5 to 6. And there was a 6 to 4. Sorry? I don't hear the question. V2, V3, V5. You're talking about on the table or the graph? In the graph? V2? What's the question? Sorry, I couldn't hear the last part what you're saying. There are some indisciplined students in this. Yeah, so your V2 can go to V5, V3, V1. That just means all those edges are in the spanning tree. Stop. There's no path. We're talking about trees. So a tree is going to contain multiple paths, right? We're not interested in path. There's a tree you're trying to build. Spanning tree. You might need to get a picture of that. Right. Okay, so that's it for Prim's algorithm and minimum, first algorithm for minimum spanning tree. Monday we'll cover, Monday we'll cover Kruskal's algorithm and then talk about Dijkstra's shortest path algorithm. All right. See you on Monday. Oh, don't forget the Google Code Jam starts tonight. Do I need to incentivize to try and beat me? All right, that's natural. You can try to beat me anyway.